Now the proof starts with by defining a norm on the space x cross y. Okay. So what is that? So norm of x y will be defined as norm x plus norm y. Now x and y are two Banach spaces, and we have defined the norm on x cross y in this way. Okay. Now the question is that whether x cross y is complete with respect to this norm. So this we want to check here, that whether this norm, x cross y is complete with respect to this norm. Okay. So for this reason, so let us suppose that, so let sequence Zn be a Cauchy sequence, in x cross y. Okay, where you can take this Zn as xn yn. Okay, so by the definition of a Cauchy sequence, you can say that, so norm of Zn minus Zm must be tends to 0 as n comma n m tends to infinity, right? And therefore, so since this tends to 0, so you can say that, so using the norm defined here, so it will be, so xn minus xm plus norm of yn minus ym, so they will be tending to 0 as n comma n tends to infinity, right? So since these are two non-zero real numbers, and adding them so after adding them, you see that this real number is tending to 0 as n tends to infinity. So therefore, so they are separately will be tending to 0 as n tends to infinity. So that means norm of xn minus xm tends to 0, norm of yn minus 0 as n comma m tends to infinity. So therefore, sequence xn, sequence ym, both are Cauchy sequences in their respective spaces in x and y respectively, right? But you have already assumed that x and y are two Banach spaces. That means they are complete with respect to their norms that has been defined in x and y. So therefore, these Cauchy sequences will definitely converge to some points respectively in x and y. So that means, suppose limit xn must be x naught, which is in x, and limit yn, suppose it is y naught, which is in y. Okay. So therefore, by the definition of limit of a sequence, so you can assert that, so x norm of xn minus x naught tends to 0, norm of yn minus y naught tends to 0 as n tends to infinity, and then by adding them you will get that the real number will be tending to 0 as n tends to infinity, and since this norm is actually norm of xn yn minus x naught y naught, so that is tending to 0 as n tends to infinity. So that means limit of xn yn is x naught y naught, so therefore it is in x plus y, and this shows that this Cauchy sequence converges. So hence, with respect to the norm defined above, so x cross y is complete, right? This is complete with respect to the norm defined above. Okay. Now consider. Now let us consider define the projection map. Projection map P from the space, the graph of the linear map T, which is a subset of x cross y, to x by. So you have chosen the first projection map, that is Px, Tx will go to x. Okay. Now, being a closed subset of a complete non-linear space, so GT must be complete. So GT is complete. GT is complete, and you can also check that this P projection map is linear. P is P is linear, and you can check that this map, this P, this is a bounded map. Why? Why it is bounded? As because of the fact that norm of P x dx so that is equal to norm x, and it is less or equal to norm x plus norm tx, right, which is equal to norm of x dx. So therefore norm of this is less or equal to norm of x dx. That means P is bounded, and norm P must be less or equal to 1. So P is a bounded linear transformation from GT to X. Okay. So therefore its inverse map, so its inverse map P inverse from X to GT defined by P inverse of x goes to x dx is also linear bounded. Okay. So therefore so this is linear and bounded. So since this is bounded, so there exists a constant m greater than 0 such that norm of P inverse x is less or equal to m into norm x, right? So that means norm of x dx is less or equal to m into norm x. Okay. So therefore norm of tx must be less or equal to norm x plus norm tx, and which is equal to norm of x dx, and this is less or equal to m into norm x. So hence, and this is true for all x belongs to capital X. So this proves that T is bounded and norm T is less or equal to m, and since T is bounded, so therefore this proves that T is continuous. Okay. The proof is very simple. We just need to check the completeness of x cross y with respect to the norm defined here, and after that you need to define this projection map, and it is complete bounded linear, the graph of T is complete, and since the map is a bounded linear transformation from GT to X, so therefore you can assert that, you can conclude that the inverse map is also bounded linear transformation. So therefore there exists a constant n greater than 0 satisfying this property, and using this one you can say that, you can deduce that norm Tx is less or equal to m into norm x, and this proves that T is bounded, and therefore in turn you can say that T is a continuous map. Okay, so this proves the closed graph theorem. ঠিক আছে? তো এই জায়গাটা একটু পড়ো, হ্যাঁ, এই থিওরেমটা একটু পড়ো। তাহলে আজকে এই পর্যন্তই থাক নাকি? প্রমাণটা হয়ে গেল, ওপেন ম্যাপিংটা হয়ে গেছে। এরপরের দিন ওইটা আমরা পড়ে নেবো যে characterization of Banach spaces in terms of absolutely the convergence of an absolutely convergent series in the Banach space. That means, so the theorem is a nonlinear space X is a Banach space if and only if every absolutely convergent series is convergent. The proof is very simple, okay, and you can define a series on a nonlinear space as like as you have defined in set of all reals in real analysis, that is xn, right, n equal to 1 to n infinity. So this is going to be a series in a nonlinear space X, and first define the Nth partial sum, that is k equal to 1 to n. This is the Nth partial sum of the series, and we say that the series is convergent in X if the sequence of Nth partial sum, sequence Sn, converges in X. So summation this converges if the sequence of Nth partial sum Sn converges in capital X, and we write the sum of the series as the limit of Sn, this, okay. And what do you mean by absolutely convergent series in a nonlinear space? A series is said to be absolutely convergent if the series summation norm of xn is convergent in the set of reals. So a series summation xk is said to be absolutely convergent in X if the series summation norm xk converges in R. Okay, and you can provide an example of a sequence in the real number space which is convergent but not absolutely, that is summation of minus 1 to the power n by n. Okay, and then you can prove the theorem. The proof of the theorem goes like this way, proof of the theorem is that suppose you first of all suppose that X be a one-arc space. Okay, and summation xk is absolutely convergent. That means summation norm xk converges, right? Norm xk converges. Now you take the nth partial sum of the series summation xk, that is summation k equal to 1 to n, and you take the nth partial sum of this series, that is summation k equal to 1 to n norm of xk. Okay. Now norm of Sn minus Sm is going to be equal to norm of xm plus 1, xm plus 2 plus xn, right, for all m less than n, and which is going to be less or equal to norm of xm plus 1 plus norm of xm plus 2 plus norm of xn. Now if you take this sum, so it is actually Sn dashed minus Sm dashed, right? Now since you have already assumed that this series converges, so that means the nth partial sum of this series converges. That means, and every convergent series is Cauchy, so therefore Sn dashed minus Sm dashed must be tending to 0 as n comma m tends to infinity, and therefore it says that sequence Sn is a Cauchy sequence. Cauchy sequence in X, but you have assumed that X to be a Banach space, which implies that since X is complete, so sequence Sn converges, that is summation xn converges. Okay, and the converse part is also very much easy to prove, because suppose the condition holds, that means suppose every absolutely convergent series is convergent, and you need to show that the space underlying space X should be complete, and for this reason you need to take one Cauchy sequence Xn. So conversely I am going to check, I am going to just, so sequence Xn be a Cauchy sequence in capital X. Okay. Now I have already so there is a problem, and you can prove this, that suppose you have taken a Cauchy sequence, then you can show that there exists a subsequence yn in X, so that norm of yn plus 1 minus yn must be less than some 1 by 2 to the power n. Okay. Okay. Now let us assume that, let us denote that y naught to be theta, theta with a 0 vector, and then what is yn? Yn can be written as y1 minus y naught plus y2 minus y1, and it is yn minus 1. Okay. So now norm of, so from this you can say that yn minus 1 is less than 1 by 2 to the power n minus 1, and if you take the sum, so n is going to be 1 to infinity, so this must be So this is convergent, right? This is convergent by the comparison test, and by hypothesis every absolutely convergent series is convergent. So summation yn minus 1 is convergent. That is, now what is summation yn minus 1? So it is sequence yn in X. আর হয়ে এসছে তো, দেরি করলে দেরি হবে কিন্তু।
তাড়াতাড়ি সবাই লিখে নিন।
Okay. So yn is convergent. Now since the original sequence is xn and yn is a subsequence of xn, so since xn is Cauchy and yn is convergent, so since xn is Cauchy and yn is convergent, so you can, so this implies that the original sequence xn must be convergent. It is also another problem. So since xn is Cauchy and you have already proved that there exists a subsequence which is convergent, so that means the original sequence must be convergent. So therefore the sequence xn was has been taken as any arbitrary Cauchy sequence in X. So therefore, so hence every Cauchy sequence converges in X. So therefore X is complete. So this completes the proof. Clear? So in a non-Banach space, that is incomplete space, absolutely convergent series may not be convergent. And if you consider the polynomial space P01 with respect to sup norm, and if you take the series, suppose you take the polynomial space this, and on that space if you take xn x to the power n by n factorial, yes, then this is absolutely convergent but not convergent. So from this you can also say that this space is not complete. Okay, আজকে এই পর্যন্তই থাকতো না।